Good evening, everyone. Welcome to the week 2 live interaction session for the course Colloids and Surfaces. Let's just wait for a few minutes for others to join before we begin our session for today. So let's just start our session for today. Let me just present my screen. I hope the PowerPoint presentation is visible as well as I'm audible. So yeah, let's just begin our session. Good evening, everyone. Welcome to the week 2 live interaction session for the course Colloids and Surfaces offered by Professor Basavraj from the Department of Chemical Engineering, IIT Madras under the NPTEL program. I am Pratyumnan, a PhD scholar at the Indian Institute of Technology. I am one of the course team member who is responsible for conducting the live interaction session for this course in this semester. So in the previous week we discussed about the fundamentals of colloid. So what just we saw in week 1 was the very basic of colloids. So now we have an understanding on what is colloid, the basic definition of colloid, the different type of applications of colloid, and also on the different types of characterization of the colloid. So if you see in the last week we discussed about many different parameters that are used for characterization of colloidal particles, such as size, shape, particle density, and then the surface charge density, and many more. So basically, if you start speaking about the colloid, as we said in the last week as well, colloids are nothing but they are just a system of particles where each particle can have at least one of their linear dimension within the range of micrometer to nanometer. So these colloidal suspensions are nothing but a homogeneous dispersion at the microscopic level, but when you go at the microscopic scale they turn out to be a heterogeneous dispersions. And then we discussed about the different type of interactions that is present between the dispersed phase as well as the dispersed medium. If you remember, when we were classifying colloids, depending upon the nature of interaction, we discussed about two different type of colloids. So I hope you guys are able to recollect what we did last week. If not, if you remember, we discussed about two colloids, lyophilic and lyophobic colloid. So lyophilic, so the word philic, as we said in the last class, it means liking. So lyophilic means the both the dispersed phase as well as the dispersed medium have a good liking for each other. However, in case of the lyophobic colloid, it's the opposite. They do not have a particular liking towards each other. The dispersed phase as well as the dispersed medium do not like each other, and then the dispersed phase tend to settle down at the bottom of the solvent. And similarly, we also saw the remedies or the ways how to improve the dispersion of a particular component, and also we saw how this particular interaction varies depending upon the nature of the solvent also. So then we discussed about the different types of characterization of colloids. We solved problems on them. If you remember, we solved approximately 4 to 5 problems on calculation of specific surface area, density of the colloidal dispersions, and then we also discussed one of the problems on surface charge density as well. So today we will again go up with solving of these problems and then move on towards the other characterization techniques, and then finally go towards the different type of forces that acts on the system and the different types of interactions that is present between the dispersed phase, and then end our lecture based on the scattering techniques that are used in the colloidal systems, followed by solving of some of the numerical problems for this week. So let me just So this is also a very similar question like how we saw in the last week. So it states that we have a colloidal suspension consisting of particles cubical in shape with a side length of 5 micrometers, and then it is also stated that this suspension undergoes further processing to form spherical particle. It is stated that the mass of the particle is 400 grams, and we are asked to calculate the specific surface area of the particle after the treatment. So let me just give you a few minutes for you to solve before we solve this problem. This is very similar to what we had discussed in week 1 live interaction session as well. So I hope you will be able to solve this one without much difficulties. So yes, here like unlike last time we use the formula specific surface area is equal to 6 by rho dp. Here it's just that instead of the specific surface area, you are required to use the mass of the particle in the system. So again, it's a very simple question, and let's just solve this quickly before we can progress for our other discussions. So the question has stated that colloidal suspension is consisting of particles which are cubical in shape and they have a particular side length of 5 micrometers. Now we are going to do some processing, and we don't have to worry about what processing it is, but upon this processing we have formed spherical particles. Now they are asked, and they are saying that the mass of the particle is 400 grams. They are asking you to calculate the specific surface area. So as such, specific surface area, whenever there is a term specific in front of any of the parameters that this has been asked, it always means that that particular physical parameter divided by mass of that particular material. So specific, let's say the physical quantity that you want to calculate is y, is nothing but that particular physical quantity divided by mass. So it's something like, in case of specific density, it is density by mass. Specific surface area by mass. So specific volume, it is volume by mass. So you can, I hope now you have the clarity. Whenever there is a word specific, it's just that the particular physical parameters following that divided by the mass of that particular substance. So here it is stated that the particles which are cubical in shape is going to undergo processing and form spherical particles. So in that case, the volume of the particles need to be conserved. So I can write conserve the volume of particles. So which means we have to conserve the volume of the cube to the volume of the spherical particle that is formed. Everybody knows volume of cube is nothing but the side length, the whole cube, or a cube. That is nothing but, here the side length is 5 micrometers. So 5 into 10 to the power -6, the whole cube. So I am writing the micrometers in terms of meter, and volume of the sphere is nothing but pi d cube by 6. So that will be 3.14 times d that we are supposed to calculate, which is not given to us. So here volume of cube is equal to volume of sphere, and since if you see in the last week over there we had similar question, but there the cubical particles was undergoing some sort of processing to form some x number of spherical particles, like 100 or 1000 spherical particles. But here we do not have any conditions like that. Here we are taking one cubical particle and that is getting converted to one spherical particle. Just a second. Some glitch in the recording software. So yes, yeah, here the volume of the cube and the volume of the sphere is going to be same, because one cubic particle is going to get converted to one spherical particle. So five into 10 to the power minus 6 the whole cube equal to volume of the sphere, that is 3.14 times d cube by 6. So if you solve for d, what you will be getting? Let me use the calculator that I have. Oh, sorry. So the value of d will be so this will be the value of d. So if you calculate, let me just use the calculator. So 125 times 6 divided by 3.14, okay, times 10 to the power minus 18. Oh, let me just use my personal calculator and check the value. Meanwhile, you can also let me know what is the value of this diameter. So it is coming out to be 6.20 micrometers, or 6.20 into 10 to the power minus 6 meters. So this is the diameter of the particle that is formed after the processing. Now we are supposed to calculate the surface area. Surface area of a sphere is nothing but 4 pi r square or pi d square, right? So we know d value is 6.2 micrometers, so that will be 3.14 times 6.2 into 10 to the power minus 6 the whole square. So which will be equal to, what will be the value of this? Times, so this is nothing but if you, it is nothing but 1.207 times 10 power minus 10. I hope I am correct. Please you also check once again. These many meters square. So the surface area of the sphere comes out to be 1.207 times 10 to the power minus 10 meter square. So now the specific surface area will be equal to surface area, that is 1.07 into 10 to the power minus 10 divided by mass in kg, so 400 grams, so that is 0.4, so it will be 3.01754 times 10 to the power minus 10. Minus 10 meters square per kg. So this is the specific surface area of the particle after the treatment. After the treatment. So previously we used the formula specific surface area is nothing but it's equal to 6 by rho dp. This is another model of that particular kind of a question where instead of using that formula 6 by rho dp, we are given the mass of the particle. So this further simplifies the problem because mass is directly given to us. So this is how you calculate the specific surface area of the particle. Now we go for the second question. It's something about calculating the mass fraction of the particle with all the density of the suspending medium, dispersed phase as well as the colloidal dispersion is given to us. So this question also we solved it in the last class. I mean a very similar one. So it's nothing but you just need to use this formula, 1 by rho of the dispersion is equal to 1 minus rho of the particle minus 1 divided by rho of the suspending medium times mass fraction of the particle plus 1 by rho of the suspending medium. So rho d is nothing but the dispersion density of the colloidal dispersion, formed colloidal dispersion. So that is 1350 1 divided by rho of the dispersed particle. So that will be this one, 1500. Oh sorry, this will be 1000. this will be this is not suspending medium, this will be dispersed particles. Dispersed phase or dispersed or the suspending medium plus 1 by 1500. So here you are supposed to calculate the mass fraction of the particle. So if you solve for this fraction, you will be getting the mass fraction of the particle as the fraction will turn out to be x is equal to 10 by 45. So that will be approximately 0.2. So the mass fraction of the particle in the dispersed phase is is 0.22. So this is a very similar question. On that day we calculated to to obtain the density of the formed colloidal dispersion. Here we are just using this formula to calculate the mass fraction of the particle. So it's just that we are solving different varieties of problems so that you get the practice and there won't be any difficulties while facing this question elsewhere. So that is the main motive of solving a similar type of question once again in the live interaction session. So yes, with this we finish our problem solving for the concepts that we learned in the week 1 live interaction session. So now we move on towards the topics that are for the week 2 live interaction session. So if you see, we have certain parameters to discuss in the characterization of the colloidal system. So if you see, we have two different parameters that was not covered in the week 1 live interaction session. So if you see, there are two. One is the surface charge density and another one is the grafting density. So if you remember, we solved a problem on calculating the surface charge density. So what is this surface charge density? It is nothing but it signifies the amount of charge that is basically present on the surface of the particle per unit area of the particle. So the charges that is present on the surface, that is, if you assume a colloidal dispersion, the charges that gets present on the surface of the particle is called as the surface charges. These surface charges are determined through the zeta potential. These surface charges are represented in the form of surface potential, which is nothing also but the zeta potential, that is calculated using the dynamic light scattering technique, which we will see in the today's lecture towards the end of today's lecture. So from that zeta potential we can calculate the surface charge density. So the surface charge density can be calculated as sigma c is equal to qc by pi dp square. So qc is nothing but is the surface charges and pi dp square is nothing but is the surface area of the particle on which this charges are stored. So if you remember the last problem, over there we discussed about the amount of charge that is present on the surface. It was given that the particular functional group has a base charge of 2, then we were asked to calculate the surface charge density. So over there was a question raised on why we are using this 1.6 into 10 to the power minus 19. So I like to reinstate that particular statement what I mentioned in week 1 live interaction session also. So these base charges that you see are not the absolute charge. You can say they are just the absolute charge that the particular functional group carries with that. But in order to find the charge, the total charge, the charge that the electrons also towards carry, you have to multiply that base charge with that 1.69 into 10 to the power minus 19 coulomb, because these base charge do not have units. So charges as such is usually represented in the form of coulomb. So you need to multiply the 2 charge or the absolute value 2 times the factor 1.6 into 10 to the power minus 19, so that is the total charge that is stored on the particle. It's not 2, it is 2 into 1.6 into 10 to the power minus 19 coulomb is present on the surface of the particle. So that I would like to once again clarify that. Now we move on towards the grafting density. So grafting density, so it has a term so called as a grafts. So what are graft? So graft are nothing but they are the long chain of molecules that are attached towards the attached to the surface of a particle. So assume you have a or we can take this example here. Assume that we have the silicon oxide particle. In order to functionalize this silicon particle or add graft, we put a long polymeric chain on its surface. This part of the structure apart from this SiO2 is nothing but they are called as grafts. So there is some specific requirement for using this graft, for attaching a graft onto the surface of a colloidal particle. So can anyone tell me what could be the reason for doing this functionalization or for attaching a graft to this colloidal particle system? Any idea? Yes, any idea on why do we use grafts for the materials, or why do we do grafting as such? So it is simple. The reason why do we do this kind of grafting is basically to improve upon the properties of the material. So by doing grafting we can help in the better dispersion of the colloidal particle, because sometimes there can be chances that it may be a lyophobic one, and by attaching chains we can actually make it as a lyophilic and help in dispersing the particles properly in the solvent, or it can also help in improving the thermal stability of the particle. And one more interesting example that you can see of doing grafting is that it has prospects even in the battery application. So batteries usually have a separator, so that separator in the energy storage field in batteries that we have a separator. The separator's role is to separate both anode and cathode, so that they do not come in contact with each other, otherwise there will be a short circuit. So that is the preliminary function of a separator. So upon grafting that separator with the silicon oxide particle, like if you see in the literature, polyethylene was used as a separator. Upon grafting silicon oxide particle on that polyethylene separator, they were able to improve the mechanical properties, adhesion strength of the separator. So that ultimately helped in improving the cyclic performance, that is how many cycles does that particular battery can run without any degradation of its performance. It was that was enhanced by doing this grafting process. So grafting process as such, it helps in improving the properties of the materials or the performance of the material. So one such example is in energy storage. Of course there are so many other examples in the literature. If you just Google grafting or the prospects of grafting, you will see a number of papers where they have done grafting to this colloidal systems or any other system to help in improving the properties of the material in variety of application, not just in energy storage. So I have just told here that energy storage, but this has been used in multiple other fields for different purposes as such. So this grafting as such, it requires mixing of both the colloidal particles as well as the grafting material, and then doing some sort of a processing so that this grafting chain is attached to the surface of the colloidal particles. But now it's not necessary that whatever quantity of the grafting molecules that I add to the system need to attach to the surface. So there comes the concept of grafting density, that is how many particles or how many grafts are attached to the surface of the colloidal particle is given by grafting density. So the grafting density, if you see, you can see the formula, it is calculated as Ng by pi dp square. So where Ng is nothing but number of the graft molecules that is attached or present per unit colloidal particle or the colloidal molecule, a colloidal particle. So this Ng, that is your number of grafts, is calculated as per the formula that you can see here. It is Ng by Mw times NAV by Nt. So here we have space. So here Mg is nothing but the mass of the graft in the system. Mw is nothing but the molecular weight of the graft. NAV, you know, it is Avogadro number. I mean, yeah, that is known. Avogadro number. Then you have Nt. Nt is nothing but the total number of particles in the system, right? Oh, sorry. So this is the explanation for each and every term. Mg is the mass of the graft in the system. Mw is the molecular weight of the graft. NAV is nothing but Avogadro number, 6.023 into 10 to the power 23 molecules per mole of the material or the compound. Nt is nothing but the total number of the particles or the colloidal particles in the system. So this is the formula. So usually we calculate this using some sort of a thermal analysis technique. If you see, there are actually two types of thermal analysis, but for calculating the number of grafts or this grafting density, we use a thermal analysis technique or thermal characterization technique called TGA, which is nothing but thermogravimetric analysis. So that technique is usually used to identify the thermal stability of a particular sample, or to be more specific, it can be used to determine how much a sample degrades at a different temperatures. Suppose if you take a particular material, if you heat it across a span of temperature, let's say from 25 degrees Celsius to 800 or 1000 degrees Celsius, you can determine at every different temperature or over a particular range of temperature how the mass of the material has decreased or has degraded. That particular trend of degradation can be identified along with accurately determining how much mass of the material has degraded. So these graphs, if you see the colloidal system particles, especially if you see like the silicon oxide, they have very high thermal stability compared to the graph. So when you heat across a particular range of temperatures, so what you can observe is that only a so what you can observe is that oh, so if you heat this particular system to higher temperature, let's say to a decomposition temperature of that particular graph that you add, the amount of weight change that happens at that particular temperature or till that particular temperature is nothing but is the mass of your graphs. So you take a sample or you take a grafted system, you know it has been grafted, you know what is the molecular weight of the graph that you have used, you know the decomposition temperature of your graph. Now you take your sample and then you heat the sample till that decomposition temperature, and you see how much amount of the material or what is the mass of the material that has been decreased compared to before starting the experiment. So that weight difference is nothing but is the mass of your graft in the system. So that is nothing but mg. Now you know NT, Na, V, Mw as well as mg. So mg from your TGA experiment. So once you know this, you will be able to calculate your value of Ng. If you know Ng, you know that diameter of the particle will be given, so you will be able to calculate the grafting density of your system. So this is about the grafting surface charge density and grafting density and the overall characterization of your colloidal particle system. Now I hope there are no doubts. In case if you have any doubts, then please let me know now, before we move on towards understanding the forces and interactions present in the colloidal particle system. Does anybody have any doubt? So colloidal particle interaction. So you have this dispersed phase as well as the dispersion medium, and those together forms the colloidal system, right? So there will be also the different forces that will be acting in between them, like between both the dispersed phase and the dispersed medium, as well as between two dispersed medium, provided that they are not too far away from each other. If suppose if you keep two different colloidal particles, or if you dilute it to such an extent that the two dispersed phase particles are very far away from each other, then each particle will be treated like an isolated system, and then the effect of one particle over the other particle need not be taken under consideration. But if the particles are present to an extent close to each other, then at least the electrostatic interactions will start occurring within the system. So the effect of the neighboring atoms on this particular atoms will be there, even if it is, you know, if it is closer to each other. So like that we will discuss about the different forces that acts on the individual colloidal particle because of various nature. So we have four different type of forces. One is your hydrodynamic force, another one is your Brownian force, another one is your gravity force or gravitational force or net gravitational force, and then the last one is nothing but it is the atmospheric pressure. So let's just start with the gravity force or the gravitational force. So if you see, when you suspend a particle in a beaker, let's say you take a beaker and then drop the particle in a beaker, depending upon the density of your particle, either it will sink or flow. Let's take an example where it has a density much higher than the density of your fluid. So you are going to drop a particle into the beaker, the particle has a density greater than that of your liquid or the suspension that is present within the beaker. So since its density is greater, it will go inside the suspending medium. So, and that is because of the gravitational force. So because of the gravitational force, the particle is moving downwards. So as it moves through the liquid, apart from this gravitational force, there will also be an upward thrust that will be acting on the particle due to this fluid. This upward thrust is called as the buoyancy force. So both these forces are in a direction opposite to each other. So the net gravitational force or the net force between the gravitational and the buoyancy forces can be represented as rho p minus rho f times their volume, that is 4 pi r cube by 3 times g. So this is one kind of the force that will be acting in the system. So predominantly two over here, one will be your gravitational force and then the other one will be your buoyancy force. Of course this will come into picture only when the density of the particle is greater than the density of the suspension medium. If it is not, if the density of the particle is much lesser than that of the fluid, then the particles will not be able to travel through the suspension medium. It will just stay, it will just float on the surface of the suspending medium. So this is gravitational force. Now let's come to the Brownian force. So when you hear the term Brownian force, you can recollect about what we learned in the fundamentals of colloid, that the colloidal particles actually show a phenomenon called Brownian motion. So what is the Brownian motion? Brownian motion is nothing but it is the it is the random motion of this colloidal particles due to their thermal energy. It is nothing, it is just that due to the thermal energy that they possess, they undergo random movement within the suspending medium. So from there originates your Brownian force. So it is nothing but the force that is arising due to the thermal collision of the suspending medium molecules with the colloidal particles. So as such, that's what is the Brownian motion, and because of that collision of your suspending medium as well as that of the particles, colloidal particles, that force that gets that originates during this collision is called as the Brownian force, and that's how it is represented also. F is nothing but kBt by r. R is nothing but the radius of the particle in the suspension medium, and kBt is nothing but the thermal energy. So if you remember, thermal energy is usually represented in the form of kBt, right? It will be in the scales of kBt. Thermal energy. So this thermal energy that the particles carry is responsible for its motion, and during its motion it collides with the particles as well as the suspending medium, and that originates a particular force called Brownian force. Kb is nothing but it is Boltzmann's constant, and I hope you remember what is the value of the Boltzmann's constant. So that is nothing but 1.38 times 10 to the power minus 23 joule per Kelvin. Or it can also be represented as R, that is your universal gas constant, times divided by Avogadro number, Na. So here R is your universal gas constant, but the value should be 8.314 joule per mole Kelvin and not 0.0821. So that is usually in atmospheric liters. Here you should use in terms of joules. So this is how you should remember the value of the Boltzmann's constant, because that is one of the important or most common parameter that you will keep that you will keep getting in your courses. So it is important to remember the value of Boltzmann's constant and the expression or the relation between Boltzmann's constant and the universal gas constant R. So as this particle undergo Brownian motion, it also undergoes a certain displacement, like because it's going under it's having some motion, right? So when it has a motion, it will cover some displacement or distance as it goes. So that is represented as xt, that is your mean square displacement, is equal to 2 times small d times capital D times t. So let me just write what it means. So x t the whole square is nothing but the mean the mean square displacement. It is basically you take the average of the displacement that it covers at different instants of time and then you square that. So small d is nothing but number of dimensions. So if the dimension is 1, it will be 1. If it is 2, d will be 2. If it is 3, d will be 3. Capital D is nothing but diffusivity, or you can also call it as diffusion coefficient, and T is the time traveled. By the colloidal particle in the suspending medium, right? So this is how you calculate the average or the mean square displacement that is covered by your colloidal particles due to the Brownian motion. So this is about Brownian force. So gravitational force, it's because of the density difference. Brownian force, it's because of the thermal energy that the particular colloidal particle carries with it. Now we come for the other two types of force, that is hydrodynamic force. So what do you understand by the word hydrodynamic force? So hydrodynamic forces are nothing but they are like kind of frictional force, and that frictional force is exerted by the fluid on the particle when it is moving with a constant velocity v. Suppose let's assume that let me just so assume that these are the chain of molecules, right? So they are moving in a suspension medium, or wait, better let me use Jamboard. Can we use So assume that this, and then you have this chain of molecules, or instead of chain of molecules you can say that you can say some sort of a colloidal particle, let it be like this. So these are here in motion, right? So each one is having a particular velocity, and as such, due to the thermal energy that they carry, they will be in motion throughout their throughout the time that they are in their solution. They will be having this sort of a thermal energy within them, and they will be keep on moving. So wait a minute. Sorry. So when they are moving with the particular velocity, with a constant velocity, the fluid particles that is surrounding, this is the fluid particles, fluid, right? So these fluid particles, they basically exhibit a frictional force in the direction opposite to their motion. So this frictional force that the liquid exerts on the particle is called as the hydrodynamic force. So whenever a particle is moving with a particular velocity, there will be a constant force that will be acting on them in a direction opposite to their motion, and that particular force is nothing but is the force exerted by the fluid particles on the colloidal particles, and that force is called as the hydrodynamic force. So this hydrodynamic force is a frictional force, and that is represented by F is equal to 6 pi eta r v. So okay, let me just write that also. So hydrodynamic force times pi times eta times r times v. So your eta is nothing but viscosity of the suspending medium, and your r is nothing but the radius of the particle, and v is the constant velocity with which the particles in the medium are moving. So this is the hydrodynamic force, and from this hydrodynamic force is, this expression is given by Stokes' law. So the Stokes' law states that the frictional force that is experienced by the particles due to the fluid can be written as 6 pi eta r v, where eta is viscosity, r is radius, and v is the constant velocity with which the particle is moving. So using this Stokes' law and Einstein's law, we get the expression, the Stokes-Einstein relationship, which is nothing but d equals kBT divided by 6 pi eta r. So this is the Stokes-Einstein relationship. So Einstein relationship states that relation you can write, or Einstein's law states that the diffusion coefficient or the diffusivity is equal to the kBT divided by that of the friction coefficient. So that states that the thermal energy divided by the friction coefficient this is Einstein's law. Stokes' law is F is equal to 6 pi eta RV. F is the frictional force. So this can also be written as frictional force is equal to frictional coefficient times velocity. So frictional force. So this is Stokes' law, which states frictional coefficient is equal frictional force is equal to frictional coefficient times velocity, and Einstein's law states that the diffusivity can be expressed as thermal energy divided by the friction coefficient. So using these two expressions, we can get the diffusivity as kBT divided by 6 pi eta r, that is the Stokes-Einstein relationship. So let me just write this here also. So F is equal to, so F by V, that is 6 pi eta r is equal to frictional coefficient, and substituting this frictional the expression for friction coefficient in this Einstein law, we get the Stokes-Einstein relationship. So this Stokes-Einstein relationship will be useful for us to determine the diffusion coefficient, or by knowing the diffusion coefficient, it will be helpful to calculate the radius, or also called as the hydrodynamic radii or radius of the particles. So that is the use of this Stokes-Einstein relationship. Next, moving on. So the last this force that we have to discuss is called as the osmotic pressure. So when these particles which are in the random motion, apart from colliding with the suspending particle and with the other particles of the same nature, like the same particles, there are also chances that they go and collide onto the walls of the surface. So the pressure at that time, or the force that the particles exert on the surface of the wall per unit area of the wall, is called as the osmotic pressure, which is given as pi pi is equal to NKBT. So N is nothing but the number density of the atoms, and KBT is the thermal energy that the colloidal particles carry in the suspension medium. So that is the osmotic pressure, the pressure that the colloidal particle exert on the walls of the surface per unit area of the surface. So this is about the colloidal the different forces that acts on the individual colloidal particle. Apart from that, there are also the different type of interactions between the colloidal particles. So there are interactions like the van der Waals forces of attraction or van der Waals interaction, the surface forces sorry, then you have the depletion forces, and then at the end you have the hydrodynamic forces also. So these are the four types of forces that also acts on the colloidal particle. hydrodynamic, van der Waals, depletion and surface forces. Now we come to the part of uh, scattering in the colloidal systems. So when you pass any kind of X-rays or neutron rays or light rays, the light or the photons present in those rays interacts with the electronic structure of the molecules, and that's what we are able to record as scattering in the colloidal system. So by doing this kind of scattering experiment, by passing the light on the colloidal system, we are able to probe the electronic structure of the molecule or understand about the electronic structure in the molecule. So usually this kind of scattering or probing is usually done by laser light, X-rays as well as neutron. So laser light for the scattering to take place. So it's not like at every point of time or whatever, whenever you pass a light through a particular molecule, the scattering will take place. The refractive index of both the refractive index for both the medium as well as the particle, it should be different for the scattering of light to take place. In case of X-ray, there should be an interaction with the electron cloud of the colloidal particle. The X-rays should interact with the electron clouds, and in case of the neutron scattering, the neutron rays should interact with it. It should interact. So in case of the neutron scattering, it occurs due to the interaction with the nucleus of an atom and the magnetic moments of the atom. So both these X-rays as well as the neutron rays are helpful in probing the structure of the molecule at the shorter scales, and that is because of the fact that their wavelength is in the nanometer range, and that also in the lower order of the nanometer range. For example, if you see laser light, it requires, its wavelength is 500 nanometer, and this S that calculates the depth range, that is how far the light can penetrate through the material. So it's in the order of just 0.001 to 0.04. But when you take it to the X-ray scattering or the neutron scattering, their wavelengths are very short, 0.15 and 0.4. So that is very short compared to that of the laser light, but then their penetration depth is very high. For example, if you see for wide angle neutron scattering, it's in the order of 10 to 50. But whereas if you see in case of laser light, it's 0.001, so that is very less. So if you use the laser light to a colloidal particle, it can only help us in knowing what is on the surface and not inside. We won't be able to get much information about the in-depth we won't be able to get in-depth information on the structure. Like beyond the surface, we will not be able to get information. So that is one of the limitations. So as such, if you see in scattering of the colloidal system, you have static light scattering SLS and dynamic light scattering called DLS. So we have that equipment name called DLS, dynamic light scattering instrument. So using that instrument, we are able to calculate the size of the colloidal particles and then the zeta potential or the surface charge potential that is present on the colloidal particles. So in case of determining the size, what you will be getting is the hydrodynamic diameter or the hydrodynamic radius of the particle. So you will be getting, so if you assume that this is the particle, since it is suspended in the medium, some of the liquid molecules will cover the surface of the particle. So due to which the diameter that you calculate from the DLS technique will be much greater than the actual diameter of the particle. So in case if you calculate the diameter or the size of a particle through DLS and another one, let's say through some kind of high resolution microscopic image like scanning electron microscope, there will be a difference of approximately 30 to 50 nanometer ranges, and that difference is probably because of or is due to the the liquid molecules that surround the surface of the particle. So since these molecules surround the radius, so the radius that you obtain through the DLS is called as the hydrodynamic size of a particle and not the size of your particle as such. And another one that you can actually calculate is the zeta potential. So over there we take a special sample holder called as a cuvette. That cuvette will have a gold plating on either sides, and then you disperse your liquid solution through that sample holder or the cuvette, and then you apply the electric field. So when you do that, depending upon the charge of your sample, the positive will get attracted to the negative surface, negatively charged gold surface, and the negatively charged particle will get attracted to the positively charged. So if there are two different types of polarity, different type of opposite charges are present in the liquid, then they will move towards either side of your either side of the gold electrodes, and depending upon the velocity of the particles moving, we will be able to calculate the surface charge potential, and from that we will be able to calculate your surface charge density. So this is the use of the DLS technique. For one is to calculate the size, another one is the zeta potential, and also you can calculate the molecular weight of a substance like polymers. So this is about the dynamic light scattering, or more often the theoretical part of the week 2 live interaction session. So now let's go on towards solving some of the problems. So there is a question, so just have a read or just read through the question, and then let's try to solve this problem. So the question goes like this. It is stated that the diffusion coefficient, so your capital D, of a polymeric surfactant in water at 298 Kelvin is given as 8 into 10 to the power minus 5 meter square per second. So this is the unit of the diffusion coefficient or diffusivity, meter square per second. Estimate the diffusion coefficient of the same polymeric surfactant in glycerol at 335 Kelvin, and also try calculating the size of the particle in the system, and they are asking us to take the viscosity of the glycerol as 10 millipascal seconds. So here you have to calculate the diffusion coefficient but of a polymeric surfactant, but in a different solvent and a different temperature. You are given with the data of diffusion coefficient of that polymeric surfactant in some other solvent and at some other temperature. So it's like you need to correlate, or you need to relate both the viscosity as well as the temperature to calculate the diffusion coefficient. So how do you do this? So this can be solved using the relationship that we saw previously, called as the Stokes-Einstein relationship. So what is the Stokes-Einstein relationship? The formula: Stokes-Einstein relationship. oh sorry. So the Stokes-Einstein relation is D is equal to K B T divided by 6 times pi times eta times R. So this is the Stokes-Einstein relationship. So here you have two solvents, two viscosities, two temperatures, and you are supposed to calculate two diffusion coefficient, of which one is actually given. So there are two ways to solve. One way is substituting all the values, calculating the value of R, and then using that value of R you can substitute, you can take that value of R and then go for that glycerol equation. You can write D2 and then substitute this value of R there. You have temperature, eta, and then you can calculate the diffusion coefficient of that surfactant in glycerol. Excuse me. Sorry. So that is one way. So the first way is obtain the value of R through the equation for water, and then use this value of R and calculate the diffusion coefficient in glycerol, right? So this is one way, but this is a pretty tedious work, because you have to take the value of kBt, which is in the order of 10 to the power minus 20, which is in the order of 10 power minus 23, and then you need to calculate the value of R, use that R again, use that value of kBt, and that will be like very tedious calculation. Instead, you can write the expression two times, one for water, one for glycerol, and then cancel all the common terms. So only the terms that will be remaining to you are the unknowns. So that will be nothing but your viscosity and then the temperature. So these are the only two parameters that will be varying, because we are not given any information about the radius of the particle in the different solvents. So whether they are going to undergo any kind of interactions, and due to which there might be a shape change. There are chances, there are systems like that where shape changes are possible, but since we are not given with those kind of any information on that, here we can assume that the particle shape as well as their size remains the same irrespective of the solvent, and then we can calculate the diffusion coefficient. So that is a simpler way, and I will be trying that here. So T1 divided by 6 pi eta 1 times R. So this will be for water, and D2 KB T2 by 6 pi eta 2 times R. This will be for glycerol. So if you see here, you have to calculate D2. So D1, D2 will be there. KB common, so they will get cancelled. 6 will get cancelled. Pi will get cancelled. R will get cancelled. So what you will be remaining is, if you divide this equation, so D2 by D1 will be nothing but T2 by T1 times eta 1 by eta 2. So you will be just left out with these 6 variables, of which you know 5 of them, so you can calculate the 6. So d2 you don't know, d1 you know, 8 into 10 to the power minus 5, t2 you know 335, t1 you know 298, eta 1 that is your viscosity of water. So what is the viscosity of water at 298 Kelvin? Does anybody have understanding on that? What is the viscosity of the water at 298 Kelvin? Do anybody remember that value? So it is what is the value of viscosity of water? It is 1 centipoise, so that is 0.001, and viscosity of glycerol is given as 10 millipascal, so 10 into 10 to the power minus 3, so 10 power minus 2, so 0.01. Again, this value of glycerol may not be 10 millipascal. Here we are taking for just practice purpose, but that value of glycerol at 335 Kelvin might be different from what I have given. So it's just for calculation purpose, for our practice purpose. So if you calculate this 0.001 by 0.01 will be 0.1, 0.1 times 335 divided by 298, 0.1124. So 0.1124 times 8 times 10 to the power minus 5. So that will be nothing but 0.8993. So 8.99 times 10 to the power minus 6, and the units is meter square per second. So units are very important, so please be careful when you solve any question. Now the question does not alone end there. They are also asking us to calculate the size of the particle in the system. So again, it's simple. You just need to substitute this value of d2 in this equation for glycerol, and then you can get the value of R. Or since R is not going to change, you can also use the expression 1 and then get the value of R. But let me use here the expression for d2. So 8.99 times 10 to the power minus 6. Again, here also we are using the Stokes-Einstein relationship only. So kb t kb times t, that is 335, divided by 6 times 3.14 pi, value of pi, eta 2 which is 0.01 times R. So R will be nothing but 1.38 times 10 to the power minus 23 times 335 divided by 6 times 3.14 times 0.01 times 8.89 into 10 to the power minus 6. I am just rearranging the variables so that you can calculate the value of R. I just brought the R in the denominator to the numerator, and then this D in the numerator or LHS side to the denominator in the RHS side. So value of R is nothing but so we need to calculate 1.38 times 335, 462.3 into 10 to the power minus 23 divided by 6 times 3.14 times 0.01 times 8.99, 1.693 into 10 to the power minus 6. So here it is 8.99. So if you calculate this, you will be getting 462.3 divided by 1.693, 273.06 into 10 to the power minus 17, or 2.73 into 10 to the power minus 50 meter. So this is the value of R. Again, here the value of R is small because the value that we took here are, just for practice purpose. So it just purely for practice purpose, so you need not worry about those. So this is how you will calculate the diffusion coefficient and diffusion coefficient of a polymeric surfactant in another solvent and another temperature, and then how do you calculate the value of D to calculate the value of R, that is your size of the particle in the system. So I hope if you have any doubts, then do let me know. Or else we can go for the next question. Next question is about grafting. So this is more of a straightforward question. It states that there are 10 to the power 10 SiO2 particles are grafted, and then they are going to be subjected to TG analysis. As we discussed, TG analysis is a technique here to determine the number of grafts or grafting density of a sample. They are saying that the weight loss in the material was calculated to be 40 grams. Diameter of the SiO2 particles are assumed to be 2 micrometers. Calculate the grafting density of the material. Molecular weight, they are asking us to take it as 320 gram per mole. So this is a simple straightforward question. If you use this formula, then you will be able to calculate. So I will be taking it from here. So this is the formula, mg by mw into Na into Avogadro number divided by the total number of particles. Mg is nothing but 40 grams. MW is nothing but 320 gram per mole. NaV 6.023 into 10 to the power 23, and MTE is also given as 10 to the power 10 particles. So this is the given data. So from there we can calculate Mg as mg by mw 40 by 320 times 6.023 into 10 to the power 23 divided by 10 to the power 10. So it's just now about the role of calculator. Then you can calculate the value of Ng. So that is nothing but so 40 by 320 is 1 by 8, so it will be 6.023 divided by 8 into 10 to the power 0.752 to this 10 to the power 23 in numerator and 10 to the power 10 in denominator, so you can cancel and write it as 10 to the power 13. So it can be written as 7.52 times 10 to the power 12 grams per molecule. These main amount of graphs are present for one SiO2 particles. Now we are asked to calculate grafting density. Again, that is nothing but Ng by pi dp square. So grafting density is nothing but Ng we calculated as 7.5 times 10 to the power 12 divided by your 3.14 times dp square. So they are asking us to calculate the diameter of the particle as 2 micrometers. So 2 into 10 to the power minus 6 the whole square, right? So that will be nothing but we need to calculate. So 2 square is 4, 3.14 times 4, 12.56. Grafting density is 7.52 times 10 to the power 12, divided by 12.56 times 10 to the power minus 12, because this 10 power minus 6 whole square, so 10 to the power minus 12. So that will be nothing but 7.52 divided by 12.56, 0.5987, 0.598 times 10 to the power, this 10 power minus 12 will go to the numerator, so it will become 10 to the power 24. So that will be equal to 5.98 times 10 to the power 23 grams per molecule per meter square. So this is the grafting density, 5.98 into 10 to the power 23 grams per molecules per meter square. So this is a very straightforward question. Here I have given all the values, your weight loss, your MW, your diameter of the particle, total number of the particles, SiO2 particles present in the system, and then you are just supposed to calculate the Ng value and then the grafting density. So this is a very straightforward question where you just need to play with the calculator. So moving to the next question, or before this we will go to this question, because this is about calculation of forces. So yeah, this is also another straightforward question. They are saying that consider a colloidal suspension of particles in water and it undergoes Brownian motion. Okay, the diffusion coefficient is given as 6 into 10 to the power minus 5 meter square per second. They are asking us to calculate the size of the particle. They are saying that the particle in the fluid is moving with a velocity of 8 micrometer per second. So 8 into 10 to the power minus 6 meter per second. So you can see how small the velocity is. And then they are saying that the density of the particle is 1050 kg per meter cube. They are asking calculate the hydrodynamic, Brownian, and then the gravitational force. So how do you calculate this? First of all, we need to calculate the radius of the particle to calculate all these forces, because if you see in all these expressions, everywhere you have R. In hydrodynamic you have R, in Brownian force you have R, in gravitational force also you have R. So you need to calculate the size of the particle before going to the calculation of forces. So as I said previously, for calculating the radius of the particle, you need to use Stokes-Einstein relationship. So let's use that. So D equals to, I hope by now people will be very familiar with the formula of Einstein relationship, because that is very important. So this is the Stokes-Einstein relationship. So the value of D is given as 6 into 10 to the power minus 5. Kb, you know, Boltzmann's constant. T is given as, since there is nothing mentioned, we can take it as room temperature. Viscosity, water, so you can take it as 0.001 times R. R is nothing but the radius of your particle that you are supposed to calculate. So yes, so taking R in the denominator to the LHS side and then bringing that D to your RHS, you will be getting yes. So the value of R is, let's just calculate, $411.24. This is 0.11304. So value of R is it is 411.24 divided by 0.11304, 3638.0042, 10 to the power minus 18, or it can be written as 3.638 into 10 to the power minus 15 meters. So this is the radius or the size of the particle. So now, since we have the size of the particle, we can calculate all the three forces. So let's just calculate that. So first is the hydrodynamic force, which is the frictional force. So that will be 6 pi eta R V. So 6 times 3.14 times eta 0.001 times R. R is given as 3.638 into 10 to the power minus 15 and your velocity is 8 micrometer per second, so 8 into 10 to the power minus 6. Again, all these are for calculation purpose, for practice purpose, so need not be very bothered about what we get at the end, unless or until we are not doing any mistakes. It's fine. 6 times 3.14 times 0.001 times 3.638 times 8, 0.548 10 to the power minus 21, or you can write it as 5.48 into 10 to the power minus 22 Newton. So this is the hydrodynamic force. Now coming to Brownian force. So Brownian force is nothing but kBT by R. So that will be kB, again Boltzmann's constant, into temperature 298 Kelvin, we can take it as 298 Kelvin, and then R is the radius, so 3.638 times 10 to the power minus 15. So what will be the value? 1.38 times 298 divided by 3.638, 113.0403 times 10 to the power minus 23 plus 15, so that will be minus 8, or it can be written as 1.13 times 10 to the power minus 6 newtons. This is Brownian force, kBT by R. Now force due to gravity. So that is rho P, that is the density of your particle, minus, let me just show, minus rho F, that is the density of the fluid, 4 pi R cube by 3 times G. So density of the particle, let me just write rho of P minus rho of F times 4 pi R 3 cube. 4 by 3 pi R cube can also be written as pi D cube by 6. Yeah. Times G. So that is nothing but rho P. Rho P is density of the particle, that is given as 1050, minus you have the density of fluid, that is water, so that will be 1000 at 298 Kelvin, times 3.14 times D cube. So D is so it is 2R, so that is nothing but 7.2 times 10 to the power minus 15 into G, that is 9.81 by 6. So I hope you will be able to calculate this. I am just going to leave it here because it's all about, I mean, it's turning more into just that, multiplication rather than anything else. So you can solve this, some Newton will come. So I will leave it to you guys so you can solve this. If you have any doubts, then please let me know now before we progress for the last two questions that we have for our session today. So if you have no doubts, then let's move to this question. So it's about finding out the mean square displacement and the diffusion coefficient. And you are given a colloidal particle of 100 nanometer diameter is undergoing Brownian motion in glycerol at 320 Kelvin. Calculate the diffusion coefficient and the mean square displacement based on the particle at t equals to 10, 100 and 1000 seconds. Assume that the viscosity of the glycerol at 30 Kelvin is 8 centipoise and consider the dimension as 2. So how will you solve this? Again, same way, you are supposed to calculate the diffusion coefficient. So for that, you have the radius of the particle, viscosity, temperature. Yes, so you can use the Stokes-Einstein relationship and then calculate the diffusion coefficient. Once you calculate the diffusion coefficient, you know the mean square displacement formula, x of t the whole square is equal to 2 times small d times capital D times t. So if you do that, then you will be able to get the mean square displacement at different instant of time. You can say the displacement at different instant of time. So let's solve this question. So using Stokes-Einstein relationship, d equals kBt divided by 6 times pi times eta times r. So you can see in almost all of the questions that we have solved for today, we are using this Stokes-Einstein relationship. So this says how important this relationship is for solving majority of the questions. So it's better you remember this equation so that it will be convenient for you in solving the problems. Again, kb 1.38 times 10 to the power minus 23 times t, so that is given as 320 divided by 6 times pi 3.14 times eta 8 centipoise, so 8 into 0.001 times r is nothing but we are 100 nanometers, so that is 100 into 10 to the power minus 9. 1 nanometer is 10 power minus 9 meters. So d value is coming out to be, please calculate along with me so that if you get if there is any mistakes that I do, or if you are getting a different answer, then we can check it once again. 441.6 So what will be the expression? D will be equal to 441.6 divided by 15.072, 29.299. 10 to the power minus 23 plus 9, so that will be minus 14, yeah, or 2.9299 times 10 to the power minus 13, and the units is meter square per second. So this is your value of D. Now you are supposed to calculate x of t. X of t the whole square, sorry, equal to 2 times d times capital D times t. So small d, that represents the number of dimensions as we discussed before. So you can see here d is number of dimensions. So the value of d here will be 2. It is given as 2. So that will make the equation two times d times t. So that will be 4 dt, right? 4 dt. So now you know d, you have t, you can calculate x of t. X of t the whole square will be nothing but 4 times 2.9229 times 10 to the power minus 13 times 10, first one, and then the second one will be same. It's just that the time is going to vary. So that will be but 4 times 2.9229 times 10 to the power minus 13 times 100, and then similarly the third one will also be the same. It's just that the time will be 1000. So I'll calculate for one, you can calculate for the rest by yourself. So 4 times 2.9229 times 10, okay, 4 times 11.696 times 10 to the power minus 12, and you have to take the square root of this to calculate the x of t, but here x of t square will be meter square. If you want to calculate the x of t, then you have to take the square root. So so that is 3.4199 times 10 power minus 6. So this is how you calculate the x of t or x of t square. So the rest you can do it on your own, because it's just about plugging in the numbers and then calculating the value of x of t the whole square, mean square displacement or the mean displacement. So I hope you have no doubt. I mean, if you have doubts, please let me know now, or otherwise we can conclude our session for today. So let me just stop presenting my screen. Sorry. So in case if nobody has any doubts, then let's just conclude our session for today. Yeah, so thank you everyone for joining this live interaction session. I hope this was useful for you. We will meet again on 11th August from 5 p.m. to 7 p.m. for our week 3 live interaction session, where we will talk more on the colloids and surfaces and the calculation of different other uh, you know parameters. I'd like to thank Professor Basavraj as well as the NPTEL team for providing me this opportunity to interact with you all on this Sunday afternoon from 5 p.m. to 7 p.m. Both the lectures as well as the video will be available to you very soon. And in case if you have any doubt, you are always welcome to email me, or you can always drop your questions in the Q&A session, and we will respond to that as soon as possible. So thank you, and let us meet next week. Till then, bye.